Hello class, this is a video tutorial on curve sketching logarithmic functions using the derivative. In the same manner, we find the critical points, intercepts, signs of functions, stationary points and their nature, as well as any possible points of inflection in order to sketch functions. So we find these critical points to sketch the function. We can apply the same concepts to logarithmic functions, as well as adding new concepts to help sketch the graph. Well, very plain and simply, we're going to be sketching this graph. The first thing we should consider are any restrictions that we might have. And if you guys remember with logarithms, or at least I hope you guys remember, the domain of any logarithm of any base, the domain of this is from 0, not including 0, to positive infinity. Or you can say just that x must be greater than, must be greater than 0. It cannot be equal to 0. You can test this yourself. You just grab your calculator, type in ln of 0 or ln of any negative value. So with that in mind, you should always keep this in mind when going further beyond this. So first, let's find the easiest points, the intercepts. I'm going to begin first with the y-intercept. And I hope you guys remember, y-intercept, x equals 0. Well, if we type in y of 0 equals, well, since it's x, it's going to be 0 times ln of 0. Normally, we would say 0 times anything is 0, but if this is 0 times ln of 0, ln of 0 is actually undefined. So let's write that down. Let's do it in a little note. ln of 0 is undefined. So there is no solution for this. So 0 times something we don't know, well, this just means that there is no y-intercept. Moving right along, let's find the x-intercept now. X-intercept. Hope we know that y is equal to 0. So now we're going to take the expression x ln of x is equal to 0. This may not seem like it, but I hope you can see that this looks like x minus a, x minus b, in that there's two factors. There's x and ln of x. Because of this, we're going to let each factor equal 0. So I'm going to let x equal 0, and ln of x is equal to 0. Well, we already know that this is undefined, so this is not a solution. But this we can solve. You can solve this in any manner of way. I'm gonna do this by changing it to index form, because remember ln is log base e, and by the definition of logs, this can be converted to be e to the power of 0 equals x. Well, e to the power of 0, that's just 1. So our x-intercept is at 1, 0. Now from this, we can create a table of signs to help us graph this function. So table of signs. And this will indicate to us where the function is above or below the x-axis. The function values that I will be using, the x values I'll be using are, well, 0 because it's a critical point, even though it's not included. So 0. And we need ln of x. Well, this one's undefined. We don't know. So we're going to leave this as blank. The next value I'm going to be picking is 1. And as we saw, ln of 1, that's 0. Well, 1 times 0, that's 0. So this is on the x-axis. Let's do half now. For this, we'll check ln of half. The value that we get is, whoops, ln, we'll just do 0.5. That's half. Negative. Okay, so this is negative. Well, this is negative, sorry, because it's x times ln of x. X is positive, so half times a negative. So this is negative. Let's test one more value. This is going to be now at 2. 2 times ln of 2, that's positive, which means that this is also positive. Now, from just this small table of signs, I hope you can visualize what the graph is already starting to look like. Here's my y-axis. Here's my x-axis. 0 is here, and 1 is here. So 1 is on the x-axis. There is actually a open interval here because it can't equal 0, but it approaches 0. So it's below like this. It goes up because from 0 to 1, it is negative below the x-axis and then positive onwards. So now let's find any stationary points that may exist. Stationary points. For this, we need the function, which is y equals x ln of x, and we need to find the derivative of this expression. For this, we're going to be doing the product rule. Just to make this easy for you, I'm going to let u, whoops, it's going to be u v plus u prime v. Let's find u is equal to x, u prime is 1, v is ln of x, v prime is 1 on x. Just substituting into our formula. Y prime, u v prime, that's x times 1 on x, that's just 1, plus 1 times ln x, that's just ln of x. To find any stationary points, we're going to let this equal 0. Solving for this, we get ln of x is equal to -1. And once again, I'm going to change this to index form. This is ln e of x equals -1. To index form, this becomes e to the power of -1 is equal to x. So x e. Now we're going to figure out the y value at that point. So y of e to the power of -1, substituting into our function. That's e to the power of -1 ln of e to the power of -1. Using index laws, this -1 power becomes a coefficient. So this becomes negative e to the power of -1 ln of e. ln of e cancels to become, that's just 1. This just becomes -1 on e. So we have a stationary point at 1 on e and negative 1 on e. Here's a stationary point. Now to find the nature of this, you can do it in many ways. I'm going to be using the second derivative for this. So my first derivative is this one here. So y prime is 1 plus ln of x. Y double prime, deriving again, the derivative of 1 is, well, nothing, goes away. The derivative of ln of x is 1 on x. Substituting our x value, the stationary point, so y double prime of e to the power of negative 1, that's 1 on e to the power of negative 1, which gives us just e. And that is greater than 0, which means this is concave up. Therefore, this must be a minimum. Oop. So 1 on e, negative 1 on e is a minimum. Last thing we need to find is any possible points of inflection. Well, if we consider this, we already have the second derivative. So y double prime is equal to 1 on x. We know this can't equal 0. Sorry, we know that x can't equal 0. So there can't be a point of inflection, because 1 on x will always be greater than 0. Okay, because now I hope you're thinking, what if I substitute 1 on negative 1? That is less than 0, meaning that is concave down, so we might have a maximum. But the domain that we have is that x must be greater than 0, because ln of x cannot take negative x value, so there cannot be ln of negative 1. That's invalid, which means that characteristic filters down to the second derivative. So we can say that since the domain is x greater than 0, or we can do it in bracket notation, okay, y double prime is greater than 0 for domain x is greater than 0. Therefore, because it's always greater than 0, it's always concave up. Now, because it's always concave up, we can draw the graph from what we know. So we can sketch the graph from what we know. So here's my y, here's my x. We know that it approaches 0 but doesn't equal 0, so there's an open circle at this point. At x equals 1, there is a point of intersection, the roots goes like this. Again, this is approximating what it looks like. This value here is 1 on e, negative 1 on e. And now, using the description of concave up, and it's always concave up, this means as this goes to infinity, because it's concave up, it will always continue to get steeper and steeper. And that there is our graph. That's y equals x ln of x. So I hope that gave you an insight into graphing logarithmic functions using the derivative. Hope to see you in the next video. Best of luck.